Alright, so welcome everyone to online study for you. A very good evening to all of you. Let us wait few seconds so more students can join. Good evening, good evening Angel, good evening Munir. So I hope that all of you are safe because the situation is very bad outside. I think now every state has announced lockdown. So I wish all of you are safe. Everyone is taking the precautions. Everyone know all the things what they should do. Okay, so shall we wait? I can see students are still joining. Good evening, Ankurna. Okay, now let me share my. It's any problem here. Alright, now I think you can see the screen. Okay, so today's topic is algorithm runtime analysis. Okay, students are still joining. Let us wait. Okay, now shall we start? Okay, let us start. So today's topic is algorithm runtime analysis. So today I think the class will be extended till 8 p.m. because this is a long topic and I want to cover the whole thing in one class. So that from tomorrow we can start a new topic. So what is algorithm runtime analysis? So first let us see this thing. What is algorithm runtime analysis? So it is the study of a given algorithm's running time. So algorithm is what? A set of code, set of instructions which are given to run a code. So it is the study of the algorithm's runtime, how much time it will take according to a particular input by identifying its behavior. You can read here by identifying its behavior as the input size of the algorithm increases. Means what its behavior changes means how the running time varies according to the size of input. So that it says that is algorithm runtime analysis. Now in layman's language we can say that how much time will the given algorithm take to run. Okay, it is just the performance of a given algorithm, or you can say it is the measure of the performance of the given algorithm. So why it is important? It is important as it tells us the efficiency of the given algorithm. If you want to find the efficiency of any algorithm, so we can do the algorithm runtime analysis for that. Now next that it is the measurement of performance of any given algorithm. So these are the basic definitions, theoretical idea that what is algorithm runtime analysis. Now let us take an example. Okay, so before going to the actual notations to find the runtime analysis, let us see some random examples. Okay, so now you can see there is a car on the screen and we have a speedometer. Now whenever you go to purchase a car, what you ask normally? You ask that what is the mileage of the car. Okay, what how much mileage will this car give? According to that you decide which to buy. Now what the person tells you, okay, let me tell you what is mileage. So mileage is nothing but how much the car can run in 1 liter of petrol. Okay, how much how much distance the car can cover in 1 liter of petrol, that is nothing but the mileage. Now you are expecting one answer, but the person who is showing you the cars, he is giving you three answers. Suppose he is giving you 10 kilometer and 20 kilometer and 50 kilometer. Now what is this? Why he is or she is giving you three different answers? Can anyone tell me? If we are asking the mileage of a particular vehicle, so how much it can run in 1 liter of petrol, so we are given with three different. Okay, are you all listening? Yes or no? Okay, average. Top of screen is not visible. Different situation, different mileage. Yes, exactly. So Priyank is very much correct, and it is because according to the situations where the car is running. Now, yes, this was the question: how much does a car runs in 1 liter of petrol? So the situations are different. Suppose it is running in city traffic. Now here it has to face more struggle in running. Now the time the engine have to work more, so it will utilize more petrol. So suppose here it is taking here it can run 10 kilometers only. Now, suppose we have a mixed environment, means at some point we are free to run like we are on a highway. At some point we are crossing through cities. So on an average, it can run 15 kilometers. And then suppose we have the best situation where we are on a highway only. So here, how much mileage it can give? It can give 20 kilometers. Now you can see it can run different type of distances with a same amount of petrol. So this is what this is according to the situation. Now in exactly the same way, okay, I think it is visual because it is visual to my student access screen. So those who are facing issues can leave and rejoin, so you can see this. Now this same thing is happening with the codes also, okay, with the algorithms. Now algorithms can measure in 3 ways. First is the best case. Okay, best case, what will be the time taken by it? Then what will be the time taken by it in the worst case? And lastly, we have a average case. Okay, so this is a rough idea that what is algorithm runtime analysis and in comparison to a mileage of a car. Now let us see what are they. So we have some notations. Okay, we have some different notations to measure the runtime of a particular algorithm. So we are going to see them one by one. So firstly we have, okay, so total we have 3 notations for measuring the runtime, for doing the runtime analysis. Okay. Now first one is omega notation. So what is omega? Now let us read it. Don't worry, we are going to learn step by step everything. So omega notation tells that this notation gives the tighter lower bound of the given algorithm. Means if we are trying to, suppose if we are trying to sort 1000 numbers. Okay, if we are trying to sort 1000 numbers, sorting means arranging in a ascending or descending order. Now we have an algorithm for that. Suppose we have written a code to perform this task. Now it will never sort it in, suppose this algorithm takes a time always greater than 10 seconds. Okay, the algorithm takes a time always greater than 10 seconds. Means what is the minimum time this algorithm will take? It will take 10 seconds. Now it can take 11 seconds, 12 seconds, but it will not take 9 seconds because it is less than. So now we can say that this 10 is what? This 10 is the tighter lower bound. So this is what I mean by tighter lower bound. Means the time cannot go beyond this. Okay, if I tell in Hindi that इससे कम time नहीं लेने वाला है हमारा code. Okay, so that it's saying. So omega notation tells that this notation gives the tighter lower bound of the given algorithm. So we can say that for any given input, running time of the given algorithm will not be less than the given time. Is it making sense or not? Give yes or no, everyone. Is it making sense? Are we on the same page? Yes? Because in the next slide, I am going to give you a question and then you have to tell me what will be the omega and different notations for that. Alright, great. So now let us move to the second notation, that is nothing but big O notation. So this is a very popular notation and heavily used. And why it is heavily used, we will understand when we will learn all of the 3. So every time we ignore these notations, omega and one more is there, but we keep more emphasis on big O notation. So this is a very important notation. Now this notation gives us the tighter upper bound of a given algorithm. Just a second. Okay, so let me write here so you can understand. This will tell us the minimum time required. Now in the same way, big O notation tells that this is the maximum time required by the algorithm. Now beyond this, the algorithm won't take much time. Now again, let us take the same example. If we are sorting the 1000 numbers, okay, we want to sort 1000 numbers. Now if we have performed some what we can say, We have taken some test and we have found that the maximum time it is taking 100 seconds. Now in the worst case also it won't exceed this 100 second. Okay, it cannot go to 101, it cannot go to 102, but yes, it can go according to the input, it can go to 99, it can go to 79. So if, even in the worst case, means if the input is very large, then also it won't execute this 100 seconds. Now, so that is big O notation. Okay, so that's why it is saying that it is the tighter upper bound of the given algorithm. Now we can see that for any given input, running time of the given algorithm will be not more than the given time. Yes, so that was what I was saying, that we can see that for any given input. So even the input is very much large, but we can guarantee that we have the big O notation, so the time won't exceed that time limit. Okay, so the running time of the given algorithm will not be more than the given time. So this is big O notation. Now third is theta notation. So theta notation tells us what? So this notation decides whether the upper bound and lower bound of the given algorithm are same or not. So okay, so it means nothing but it will just give you the average time taken. Okay, you can see here in the second point we can say that for any given input, running time of the given algorithm will be on an average be equal to the given time. So theta notation just gives us the average, what will be the average time. So this is the I can say maximum time required. This is the this is the minimum time required given by omega notation, and big O notation gives us the omega gives us the minimum time required, big O notation gives us the maximum time required, and theta notation gives us the average. Alright, so now if I ask you a question that if we are doing a coding, again the question which we did yesterday, so you have to tell me now. Okay, now if we are doing a coding for airbag system, again in the car which opens on accident, now the efficiency should be measured in terms of which of the notation? Can you tell me, anyone? Among this omega notation, big O notation and theta notation, which should be used? Okay, I can see one answer. What about others? Some are saying omega. Okay, and anyone more want to try? Alright, just think the definition. Okay, we all know that the answer will be between 1 and 2 only, because theta is not at all required. Now, among omega and big O, in which terms should we measure the runtime of the, means in how much time will it work, the airbag will open? Okay, so many of you are giving answer big O, many of you are giving answer omega. So those who are giving omega answer are wrong. Why? Let me tell you. The answer is big O notation. Okay, so we will measure the efficiency of the algorithm in the terms of big O. Now why? Because we will also always think about the worst case. Okay, in the worst case, how much time it will take to open the airbag in the worst case. So we have to check the maximum time required. We don't have to do anything with the minimum time. Okay, but we have to check the worst case. In the worst case scenario, suppose the airbag opens in 2 seconds. It is the worst case. Now it should not go beyond 2. It should not go to 2.5 seconds. That we have to make sure. So we have to check the upper bound for that. So that's why we are checking the big O notation. Okay, are you getting? Because we need to know that in the very worst case, how much second does the system take to deploy that airbag in the case of any accident. So is it making sense, those who are telling omega notation? Now that's why practically also whenever we will study any data structure or any code, even in the examinations when you face placement exam, always they ask what is the big O notation. When they ask complexity, it is always measured in terms of big O notation. Means in the worst case, what should be the maximum time taken by the algorithm whenever we will do data structure like stack queue. Okay, every time when we will try to calculate the complexity, I will only tell the big O notation. Okay, because that is the only thing which you should know. Now shall we move forward? I am going to give you an example. Are you guys ready? So I am going to give you a operation, a linear search. You have to tell me that what, okay, let me show the screen. Okay, you can see this is an array. Okay, first listen the question. This is an array, and we have suppose a lot of numbers here. Suppose we have 1 million numbers, or 1 million numbers here. We have 1 million numbers here. So this is a very huge array. Okay, array of integers. Now, what we have to perform? We have to perform linear search. Linear search means what? We have to go cell by cell. Suppose we want to search 41. Okay, suppose we want to search 41. So we will go cell by cell. Is it matching to 41? No. Is it matching to 41? No. Is it matching? So in that order, suppose 41 is found here. So the algorithm, the code will stop here. So this is a linear search. Everyone knows this. I hope. What is a linear search? When we search an element in an array. Now for this algorithm, so for a linear search algorithm, suppose we want to find a number in this array. Now you have to tell me what will the omega time complexity in the terms of omega. You have to tell me the time complexity in the terms of big O notation, and you have to tell me the time complexity in the terms of theta notation. Okay, not like this. Just tell me with the notations also. Okay, you can write like this, that omega equal to this, big O equal to this, and theta equal to this. Like this you can write. Okay, so let us go one by one. Alright. Okay, let us go one by one. What will be the omega notation? I want to answer for everyone. Whether it is wrong, don't worry. You will learn something new. I can see 3 answers. Just think. What was the definition of omega? You can recall it. Okay, let me tell in a simple language that it will be the minimum time required to search an element. Now for that, what you have to do? You have to check a best case. You can take a best case scenario. You can imagine a best case scenario. Then you can apply. Alright, now I can see many answers. And almost everyone is correct. So the omega notation will be not big O. It will be omega of 1. Why? Now what will be the best case scenario? The best case scenario will be that if we are searching 5 in this array, now it will take how much unit of time? You can see one cell is taking suppose 1 unit. Now in searching 5 it is find at the first cell only. So it will take big O, omega of 1 time to search that. So this is the best case. Now it can't go less than this. Okay, it cannot go below this. Minimum time to search, yes, that is the correct word. Minimum time to search an element in this array, in the given array, is omega of 1. Now next thing let us do, you have to tell me what is the big O notation. Just recall the definition for big O, then imagine a particular scenario, then answer me. Okay, I can see answers coming. Let everyone try it. Okay, now I think everyone is understanding it clearly. Okay, so now big O, what it tells us? It tells us the maximum time taken. Now for that, what we can do? We can imagine a worst situation. Now what worst situation can be? This, if we are searching the element 10. Now it is found at the last cell. For that, we have to traverse this whole array from beginning to the end. So it will take how much time? It will take that many units of time as we have the number of elements, that is big O of n. So this is the time complexity in the terms of big O notation. Now lastly tell me in theta notation. So it is very easy to imagine. Okay, great. Yes, you all are correct, guys. So it will be theta of n by 2. So this is the notation in the terms of theta. That is the average time. Means any suppose we are taking for 8, we are taking for 54. So they must be around a value of theta notation. So this is average of all the possibilities. So shall we move further? Now we are going to see. Let me check. Okay. So one important thing that you should note is that for academic purpose, we need to know all these 3 types of notations. Academic by me, which I mean that for subjective exams, like in BTech you have semester exams. For that purpose, you need to know all these 3 notations, their definitions, and how you find them. But when it comes to the point of interviews and examination, what we are mostly concerned about is the big O notation. Okay, so we are only going to see big O notations for all the algorithm which we are going to cover, all the data structures. Okay, and in real life also, in actual also, we rarely ever go for theta and omega notations. Yeah. No, empty column doesn't denote missing value, Sanjay. I've already told that we have a lot of numbers in this array. Suppose we are having 1 million numbers here, 1 million numbers here. So the total elements in the array are total approximately 2 millions. Okay, so there is a huge array. So that was what I was telling. Yes, I've treated that whole course in that point of view only, in the terms of placement. Okay, so now we are going to see that how we can find the algorithm of a code. So I have written some sample codes for you all. Okay, now see two types of codes. We can find complexity of two types of code. Either it is a iterative code or it is a recursive code. Okay, before that, let us understand how many types of complexities are there. So, okay, we are talking in the terms of big O notation. So here are some examples of the algorithm runtime analysis. Okay, so first we have order of one. Now order of one are for constant statements. Suppose we have a operation like insertion node in the front of a linked list. So in linked list, I'm not going to deep of linked list. Suppose it is like an array, okay, and you want to insert something at the end of the array. So it can do it in one step. It is order of one. Suppose you know the index also. Okay, so that when we study linked list, then we will understand this example. But those operations which can be performed in 1 unit of time have the complexity order of one. It is known as constant. Now next we have this logarithmic time complexity. It is order of log n. Now suppose we are doing binary search. These are examples, random examples which we are going to study. Okay, these all things we are going to study at some point. Now binary search in a sorted array. When we perform binary search, the time complexity for that is log of n. So okay, so whenever you will find a time complexity, mostly they will be one of these. Of any algorithm, they will be one of these. Now this is called logarithmic. Then we have linear, that is order of n. In linear searching, just now which we did is a linear search, that is order of n. Now we have n log n. So when we do merge sort, we get this time complexity. It's called linear logarithmic. Then we have order of n squared, it is quadratic. Suppose we are printing elements of 2D array, so we use two loops, okay, nested loops. Then order of n cubed, when n cube is called cubic when we do matrix multiplication. And 2 power n, order of 2 power n, this is the what we can say largest time complexity. Okay, this is the worst time complexity, means the code will take a large number of time. When the input increases, the time complexity increases very heavily. So it is called as exponential, and we have a problem which we will study in algorithms, I think. Its name is Tower of Hanoi. Okay, so that takes its time complexity is order of 2 power n. Now let us contrast between all these time complexity. Now yes, for that we have a graph here. You can see. So just take a look at the graph. Now here below, okay, so in the x-axis we are having elements. Okay, elements means the input size. When we are increasing the input size for a particular algorithm, and on the y-axis we are having operations, means how many operations is used to be performed, or we can say directly that how much time is going to take. Okay, now first we have order of one. So you can see it is the fastest time, okay, because it is constant, in one step it is done. So it is denoted in a deep blue line, and I think you cannot see, but there is a small deep blue line hidden along the x-axis. So you can see whenever the number of operations are increasing, okay, if the number of input size is getting larger and larger, still the operations is 0 only, okay, so it is constant only. So with the increase in the input size, it is not varying. Now again we have a order of log n. So this is also good. I won't say that it is bad. It is also very good if the algorithm takes order of log n time. So then also it is good. You can see this is also along the x-axis. But if you stretch this x-axis further, it will slightly go above the x-axis. But still you can see here both order of 1 and order of log n are overlapping the x-axis. So these are very fast time complexities. Now let us move forward. Now we have order of n. So this you can see in green color. Okay, this line. So with increase in input size, slowly and gradually the operations increases, but still it can be considered as a fairly good time complexity, because the operations are not rapidly increasing. Okay. Now, but when we move further, we have n log n. So what was n log n? N log n is called as linear logarithmic. Now you can see this is the color. Yes, this line is for linear logarithmic. Now from here you can see it is when we increase the input size, the elements are increasing, then the operations or the time taken is increasing more rapidly. Now in the same way you have order of n square. Next, so this order you should remember, fastest to slowest. Sometimes you are given short algorithms in exam and you have to tell which algorithm is fastest. Now if you can calculate and if you know this relation, then you can that I will tell when we solve some questions. Okay, you will see. I will give you algorithm and we will derive them. Nandita, don't worry. Then lastly we have 2 power n. Then in the same way the complexity for the slowest is order of n factorial. Okay, this is the slowest. So you should remember this order of fastest to slowest. Okay. Now I am giving you some codes and let us find out the complexity for those codes. Okay. So first I am going to show you some iterative codes. Then we are going to see some recursive codes. So shall I move further, or if you have any doubt you can ask here. Shall we move? No doubt. Great. Okay. So this is the first question. Okay. We have to find the time complexity of this iterative algorithm. So you can try it. Then I will do it for you. So here we have a simple for loop. You can see we have a for loop inside which we have a if else block. Okay, you can see some answers. Okay, great. So I can see answer order of n. Now let me tell you the proper way to do it. Okay, so this the method which I am going to show you. This only you can follow to find the complexity of any algorithm which is of iterative nature. Now it is inside a function. You can see this whole thing is inside a function. Now if we consider the time complexity of the function as t of n, n is what? N is the size of this array. Now t of n can be represented as, now let us go line by line. Okay. So I know that all of you know this, but still let me solve it for you. So this line will have a complexity of order of 1 because it is a single step. Now you can see this line will have a complexity of what? It is going from 1 till the end of the array. Now it is nothing but order of n. Now these are what? These are order of 1, but these are repeated for order of n times. Now together can I write this as order of 1 plus order of 1 and this whole thing into order of n? Is it making sense or not? This is the actual time complexity for statement from here to here. Is it making sense? This line. Yes or no? Give me a reply. Yes. Now lastly we have a return bit. It is nothing but order of 1. Now if this whole thing is inside the function, so now can we write that t of n is nothing but this plus this whole thing plus this thing. It is nothing but order of 1 plus, now order of 1 plus order of 1 can be written as order of 2, then it is into order of n. Now since the constant terms we can ignore. Why we can ignore? Because this, suppose if this n is very large in the worst case scenario, since it is in terms of big O notation, so in the worst case scenario if n is suppose trillion and billions, then this order of 2 is nothing in front of it. So we can just ignore this part and this part, so it is nothing but order of n. Alright. Yes, it can be written as 2 into order of 1. Okay. So this is order of n. Now I'm giving you the next code. Just try to find the time complexity. Okay, you don't have to perform for simple codes. You don't have to perform this. But suppose if the code is much complicated, then you can use this technique. So this is the next code. Tell me what will be the time complexity for this code. Which if part? You can see if part is order, it is in single step. Okay, it will take 1 unit of time. So it is order of 1, order of 1. So this order of 1 is repeated for order of n, and we can eliminate the constant terms. So that's why I have eliminated that. Okay, it is negligible in front of order of n. Okay, I can see everyone is giving the correct answer. That is order of n square. Now, what we can write? This part is order of n, and the whole thing inside with this will be multiplied with order of n. Now, can we write it like order of n into? Now, what we have inside? We have another order of n. So this is into order of n. Then inside we have a statement which is order of 1. So this is multiplied with order of 1, and this system.print is also order of 1. So this is added. You can see it is not inside the loop, so we will add this with this. So just let me erase this. Okay, so this was multiplied with order of 1, which is for this print statement. Then we have an addition with this print statement, that is order of 1. Now after eliminating the constant terms, what we will have? We will have T of n is equal to order of n into order of n, which is nothing but order of n square. Okay, big O of n square. I am telling order. Okay, it is called big O of n square. So I hope that it is making sense. These are simple. Now gradually we will try to move to difficult questions. Okay, now try to find the time complexity. This is also iterative algorithm. I want everyone to give correct answers now. Okay, so see this carefully. Okay, so that's why I was telling that, see it carefully. Okay, so good. I can see maximum are giving correct answers. Let others try also. Let us wait for a few more people. Let me check how many of you are in the class. I can see 40 people. Okay, great job guys. You all are correct. Now you can see this for loop is having one for loop. So we can write that order of n into this for loop is nothing but order of n. Okay, the order of 1 we can ignore it. Now this for loop is order of n. So are they nested? No. So we will add them up. So we can write here order of n plus order of n. Now we have a print statement. So we will add. We can ignore this. It is negligible. So now this is what order of n into 2 into order of n. Again I am saying order. Okay, it's big O of n. Big O of n. Yes. Now it will be nothing but 2 into big O of n square. Now this 2 can be ignored, and the time complexity for this algorithm will be big O of n square. So now it is clear, I think. Find the time complexity for this one. Okay, I think you should tell why we ignore 2, because it is a constant term. Okay, let me tell you. If we have something like order of n minus 1, so we can ignore the minus 1. It can be written as order of n. If we have something like order of 2n, okay, this is similar to 2 into order of n. Okay guys, whenever I am telling order, just understand that it is big O of n, because I have a habit of telling order. So this can be considered as big O of n. If we have something of big O of n by 2, this can be considered as big O of n. Now if we have something like big O of 10 or big O of 1000, so this is nothing but big O of 1, and it can be easily ignored if we are having more terms in the terms of n. Alright, So yes, everyone is correct. You can see we have for loop, for loop, for loop, which all are nested. So that's why, and all are running. So we are having in the worst case order of big O of n cube as the answer. Now why this is we are saying it is because we can safely enumerate the constant terms. Why? Because they are negligible when they are compared to big O of n or any of its uh, like n cube or n square. Okay. Alright, so shall we try another question? Alright, now let us see that how we can find the time complexity of iterative algorithms. Not iterative, recursive algorithms. Iterative we have covered just now. So this is our first recursive. So I think we have done this yesterday also. You all know what is the time complexity for this. So I am going to use the back substitution method. Okay, I was telling masters, but masters, whenever I was trying to tell masters, it was nothing but back substitution. So I'm going to teach what is back substitution method. This is the easiest method. Okay, it is the easiest method. When you will study in academic, you will learn what is master's theorem, but those are theoretical part. Okay, those are just to create the answer lengthy for 15 marks question. But when it comes to solving competitive exams for placement, this is the best method. Okay, I can see order of n. So we all know that it is order of n because in every term we are going iterating to the one previous element. Now let us see the back substitution method. So now first we have to write the expression. Okay, we have to write the time complexity expression. Now if we follow that same technique, so this is considered as T of n and the internal thing will be the result of this. So this is equal to what? This is order of 1. So order of 1, this is order of 1 plus order of 1, that is big O of 1. Again big O of 1. Then now here you can see we are multiplying n with factorial of n minus 1. So this factorial is again time complexity will be what? T of n only. But we have n minus 1. So time complexity for this part will be what? T of n minus 1. If time complexity for this factorial function is T of n, then time complexity for this factorial function call will be T of n minus 1. Priyam, that is a part of core Java. You can check it on internet. If I start teaching that part, it will take a lot of time. I have a lot of things to cover today still. Okay, if we get time, we will discuss that. So yes, let us get back. It is important to understand this. Okay, so just see it nicely. So are you all agreeing that this part is T of n minus 1? So we can write it like T of n minus 1. Now this whole thing can we compress it like T of n plus T of n is equal to order of 1 big O of 1 plus T of n minus 1. So this we have as equation 1. Is this making sense? Is it clear? Any objections in this part? I'm waiting for replies. Yes or no? Okay, great. What about others? I can see only replies for some few students. That is Sahil, Priyank, Divjal. Okay, great. So I am keeping this as equation 1. Let me clear everything because I have to write a lot. So I am going step by step, but when you will have practice, you can do it in one step only. So T of n we have obtained that it is big O of 1 plus T of n minus 1. Let us keep it as equation. Let me see if I have a blank page. Yeah, I have a blank page here. Okay, let me do it here only. So we have obtained T of n is equal to big O of 1 plus T of n minus 1. This is our just a second, guys. This thing is our equation 1. Now we want what is step 2? Step 2 is that just look at this recursive code. You have to find the base condition. Okay, so what is the base condition? Can you see? So yes, you can see this is the base condition. Now here what you have to do, you have to check that for what value of n reckoning will not happen. Are you getting? What will be the value of n here so that reckoning will stop? Means this return function will work. Can you tell me what will be the value of n? For which value of n it will happen? Anyone? 0. Okay. So if we take the first value which will come while decreasing is 1. You can see if it is 1 also, then its condition will be true. So I am taking n is equal to 1. Now when n is equal to 1, what will be the time complexity of this entire code? Can you tell me when? So I can write t of 1. What will be the t of 1? What will be t of 1? Okay, tell me, is it order of n? Is it big O of n or big O of 1? Okay, good. Okay, good. We are going good. So we have our second observation that t of 1 is big O of 1. So we are keeping it with us. Okay. So we are keeping it here that t of 1 is nothing but big O of 1. So this is our base condition. Now let us move forward. Now from this you can see in this equation 1, what we have to do, we have to eliminate this term t of n minus 1, then only we can find the complexity. So let us find out t of n minus 1. So how can we find? You can see if we put n minus 1 in equation 1, so what it will become? It will become order big O of 1 plus t of n minus 1. If we replace this n with n minus 1, what it will become? It will become n minus 2. So this is equation 2. Any objections in equation 2? Is it clear how I found equation 2? I am going very slowly so you can understand. Okay. Now if you have any doubt, just ask at that point only, because I cannot go back. Otherwise the link will be broken. Okay, great. Now in the same way, I have to eliminate this n minus 2. So I will found t of n minus 2 using the equation 1 only. Now I am replacing n with n minus 2. So this is big O of 1 and this is t of n minus 3. So let it be equation 3. I hope this is also clear to all of you. Now from 1 what we have, from 1 let me use a different color. So from equation 1 we know that t of n is nothing but big O of 1 plus t of n minus 1. Now let us substitute equation 2 in equation 1. Okay, so we are substituting equation 2 in equation 1. So what it will become? Big O of 1 plus, we are replacing this t of n minus 1 with this whole thing. So it is again big O of 1 plus t of n minus 2. Is it clear? So this is what? This is let it be equation 4. Now again we have to eliminate this t of n minus 2. So we are doing equation, we are putting equation 3 in equation 4. So this will give us that t of n is nothing but, okay, so I am writing this whole thing as big O of 2. So big O of 2 and we are putting this 3 in equation 4. So it is nothing but big O of 2 plus big O of 1 is nothing but big O of 3 plus t of n minus 3. This is, let it be equation 5. Is equation 5 clear? What does t represent? T represents the time complexity of the entire algorithm. Okay, you can see here, initially only I have told that I am considering that the time complexity is t of n. So if this is t of n, time complexity of this function call is t of n minus 1. Alright, now by substitution method I have found this equation 3. Okay, now can you generalize the equation? You can see t of n is order of 1 plus t of n minus 1, order of 2 plus t of n minus 2, here big O of 3 plus t of n minus 3. So if we generalize this expression, it will become what? It will become nothing but t of n is equal to, suppose if this is k, this whole thing if I am considering as k, so k plus t of n minus k. Is this making sense? This is what? This is a general expression. Okay, this is a general expression. Yes. Now what thing is left? So in this we have to eliminate what? We have to eliminate this t of n minus k, and we have one thing with us which we can use. Now we have t of 1 as big O of 1. Now if we can make, let me have some space at the right side so I don't have to grab anything from the screen. Okay, I'll erase this thing. Okay, I think it will fit. Okay, now we can, if we can convert this t of n minus k as t of 1, our work will be easier. Now how we can do that? So we have to convert this n minus k equal to 1. It means what? We have k will be becoming what? K will be becoming n minus 1. So if we replace k as n minus 1, sorry, if we replace k as n minus 1 in this general expression, so let us substitute that. So we are putting this in general expression. So this will become t of n is equal to, now we are replacing k with n minus 1. So k will become n minus 1 plus we will have t of n minus 1. So when we will do, okay, t of n minus k, so it will become nothing but t of n minus k, and minus of k is nothing but minus n plus 1. So this is nothing but n minus 1 plus this will be removed and this is t of 1. So it is nothing but n, this 1 we can ignore in the terms of n, okay, because it is a constant. So n plus t of 1, so n plus t of 1 is nothing but big O of 1, so big O of 1. This also we can ignore. So lastly t of n is nothing but big O of n, which is the time complexity of this algorithm. Now, any confusion? Okay, so t is the time complexity. Okay, t is the time complexity of this code. Now big O is the notation which I am using to find the time complexity. Step by step you can see I have taken that this will be the whole time complexity. I have just assumed it. It will be big O, and time complexity is expressed in the terms of big O, this you know, and time complexity I am denoting with t, and the parameter which I am accepting as n. Okay, are you getting? Nandita? Okay, great. So this how you can see we have obtained time complexities big O of n. Why n minus k is equal to 1? Okay, so I want to eliminate this term here. I want to eliminate this term. So for that, how I can eliminate? We have one result that base case we have as t of 1 equal to order of 1. So somehow if we can make t of n minus k as t of 1, so we can use this result. So for that I am using n minus k as 1. If this was something else, we would have equated it with value present here. Okay, we will see more examples, don't worry. So for that I am writing like this. So this method is known as back substitution. Okay, it won't take so much long. I am to solve it. If you have a practice, you have to just, by seeing the code you will get this expression. If you get this expression by 2-3 substitutions, you will get a general expression, and by using the base case you can eliminate the term, the time complexity term, and you can obtain the time complexity. Now master theorem is a very long process. Okay, it is a theoretical and it won't it is not more of what I can say effective method to find a time complexity. Still I will give you some links in the announcement, you can check there. Okay, so now let me show you one more question. Will you do it? Will you solve one question? Okay, let us see, can you solve it or not. This is the binary search. I hope you all know the answer. Now try to check if you are getting the answer for this. You can see we are having recursion. How we are having recursion? Okay, let me explain you this code first. Most of you, I think some of you don't know binary search. What is a binary search? Suppose we want to search an array in a element in an array. Okay, correct, Priyank. Let us understand this code first, then we'll move to algorithm. Then we'll move to complexity. Suppose we have a array of elements, and the elements are sorted in order. Suppose 1, 2, 3, 4, 5, 6, 7, 8. Now we want to search an element. Suppose we have to search element 7. Now this array which we have here. Left is the index of the left position. So this is left. Its index is 0. We know in array index starts from 0. And this is the last index. This must be 7. So L is 0. R is 7. Now X is the value which we want to search. So this is nothing but 7. Okay, 7 again. Now first we are checking that right is less than left. So you can see what is the base case here. The base case is this part only. Okay, this whole thing will be repeated until this situation is true. So when you can see at every point we are moving right and left. Okay, you can let us solve this pseudocode with an example, then we can understand this. So this is array. This is the index 0, 1, 2, 3, 4, 5, 6. Suppose we want to search element, that is 1. So x is 1, left is 0, and right is 6. And the array we are having here. Now is right greater than left? So yes, right is 6. This is the right. This is the left. It is greater than 0. Now we are calculating mid. Mid is equal to left plus right by 2. Now what is left and what is right? It is 0 and 6. So 0 plus 6 by 2 is nothing but 3. So now we are having this 3, index 3. This is the index 3. This is pointed by mid. X is the element which you want to search. Okay, we want to search an element in this array. Now for binary search, the array must be sorted. So we have taken a sorted array, and the element which you want to search is 1. Now if the mid, the element located at the mid position is equal to x, what we will do? We will return that number. So now is it equal to 1? No, it is equal to 4. So let us go to the next if statement. If it is greater than mid, is it greater than, is the x value less than the middle element? So 1 is, yes, 1 is less than the middle element. So we are calling the function binary search again for these parameters. Again the array is passed, the left index is passed, but the right, in the place of right index, you can see the right index we are passing mid minus 1. It means mid is shifted to one step before. Now why we are doing this? You can see 1 should be present on the right side or left side. It should be present on the left side because it is less than 4. That's why we are decreasing the search space. Now what is our new search space? When this function is called, it is 1, 2, 3. Now this is already left and right is updated to mid minus 1. That is nothing but, this is second index, this is fourth index, this is the mid. Now again this function is called. Okay, so let me erase this part. Again this function is called. So from here control will go to this function again, and left is what? Left is 0, right is our mid value has become right. Okay, this is the right value. So this is the right value. So it is nothing but 2, and element to be searched is the same value. You can see the same value has been passed here. So it is nothing but 1 again. Now we are finding mid as left plus right by 2. So 0 plus 2 by 2 is nothing but 1. Now this is index 1 is the mid term. Okay. Now what we want to do, we are checking, is it equal to the value to be searched? No, 1 is not equal to 2. 1 is less, so yes, 1 is less. So what we are going to do, you can see this condition will work, and again this function will be called. So what is our new search space? Mid will be, left will be left only, and right will be mid minus 1. So our new search space is 0, and mid is coming to this place. So only one index is considered, and element is 1. Okay, now left is also this only, index 0, and right is also index 0 only. And when we will find the mid, mid will be also index 0 only, and the value will match. You can see value is matching. So it will return what? It will return the mid element, that is, it will return the index, that is, it is found at index 0. So answer is correct, 1 is found at index 0. Now suppose if it was not found, so beyond that, beyond this statement, what was happening? The left will become greater than right. So the control will not go inside this if block, and it will return minus 1, means the value is not found. So this is how a binary search works. Let me see the time. Okay, we will take half an hour more. Okay, so this is how a binary search works. Is it making sense? Now can we find the complexity, or shall I repeat how it works? Tell me, shall I move to the complexity part? Anyone give a quick yes or no? Okay, so now let us again consider that the Okay, don't worry. When we are going to study in the sorting and in the searching part, in the searching algorithm part, we are going to write this whole code again. So there you will understand this. So this we can consider as T of n. N is what? N is the size of this array. Now this if is or big O of 1, this is big O of 1, this all are big O of 1. Now here you can see we are dividing the whole array into half part. Okay, suppose this was the original array. If the element is greater, if the element is greater than this value, we are considering this part, otherwise this part. So again in every step, we are dividing the array in half and lastly we are finding the element. So what we can say here, this is what? This is nothing but T of n by 2. Okay, the time complexity for this function, this binary search function. Again the time complexity for this binary search function is T of n by 2. Now if we add both of them, it is nothing but 2 into T of n by 2, which we can call as T of n by 2 again. Okay. Now what will be the expression which we will get from this? If we add up all of this, so this is T of n, it is nothing but big O of 1 plus T of n by 2. So is this equation clear, everyone? Then we will move to the back substitution method to find the time complexity. Okay. Now I am writing this again. Now till then you can tell me what will be the base condition. So this we have as equation 1. What will be the base condition? This is our equation 1. Okay, check here. What will be the base case? It means what? When this recursion will stop for what value of n? Now what is n? N is the size of the array. So what will be the last size of the array after which recursion will stop? That I am asking you. It is a logical thing. Sometimes you can see it directly in the code. Sometimes you have to think of it. Okay. Now let me help you. So this right and left are moving from their positions. Suppose initially we have 1, 2, 3, 4, 5, 6 cells. Next we had 3 cells. Next we had 1 cell. Now beyond 1 cell, what will happen after this 1 cell? It will stop. So what is the last value of n? So time complexity of last is big O of 1. Is this line clear? Because at last we will have only one cell, because both right and left will be pointing to that one particular cell only. Okay, so if the size of array is 1, it will take how much time to search that element? Suppose we have taken an array, it is storing 1 and it has only one element. Now my question is that you have to search an element 1 in this array. How much time it will take? It will take order of 1. Suppose I am telling to search 10 in this array, it is not found. And how much time it take? It took big O of 1. So is it clear that T of 1 is big O of 1? Everyone agrees to this? Just a second. Okay. Yeah. So let us do that same technique. So we have the base condition as T of 1 is big O of 1. So this we will use later when we will get the general expression. So this is the base condition. Okay. Now we have to eliminate this term T of n by 2. So what we can find? We can find that T of n by 2. What is the time? 17. So T of n by 2 is what? T of n by 2, if we put in this, so we can write it as T of n by 4 plus big O of 1. Is it clear? I think it's clear. We are substituting n as n by 2. Now in the same way, if you want T of n by 4, so T of n by 4 is nothing but T of this n will be replaced with what? This n will be replaced with n by 4 and it will become n by 8 plus big O of 1. Let this be 2, let this be 3. Now T of n, after we will substitute this 2 in equation 1. So what we will get? We will get as T of n as T of n by 2 plus big O of 1. Now next, if we substitute, alright, so this was the original equation 1. Now if we substitute this equation 2 in equation 1, it will become what? It will become T of n by 4 plus big O of 2. Okay, and now if we substitute this 3 in this part, means if we replace this T of n by 4, so it will become what? T of n by 8 plus big O of 3. Now I think you can understand what is the general expression. You can see when this is 1, it is 2. When this is 2, it is 4. When this is 3, it is 8. So it is what? It is nothing but the power of 2. 2 is getting multiplied every time. So what will be the general expression? So in terms of k, we can write it as T of n by, can you tell me what will be here? What will be this part? You have to tell me. If this is k, what will be this part? Okay, everyone agrees with Priyank. You can check the comment. Priyank has given. Okay, all right. Everyone is giving the correct answer. 2 power k. So this is our general expression. Now what we have to do? You tell me what we have to do next, everyone. This is our general expression. So what is the next step? Compare with BC. So we have to eliminate this term. So you can see we have a result as T of 1 as order of 1, big O of 1. So can we somehow make this as 1? So how we can make that? So n by 2 power k is equal to 1. It means what? N is equal to 2 power k. Now I think you have learnt in mathematics that if you apply log on both sides, so we will get what? K is equal to log n base 2. So is this part clear? Now we are putting this in the general expression. We are applying this k. We are substituting this k in the general expression. Okay, so this will become T of n n by 2 power 2, just a second. Okay, this will become T of 1 plus k. We can replace this k with log of n base 2. Now T of 1 is what? Order of 1. You can see from here, and we can easily eliminate this. So we get T of n as log of n base 2. Is it clear? So this is the time complexity as order of big O of log of n base 2. Is this clear? Everyone just check it. Is it crystal clear or not? Any doubt? Ask me. I am giving you 1 minute. Just check it. Everyone, I am asking with everyone. Alright. Is my explanation clear? If you have any problem with my explanation. Okay. Now, can you tell me what is this 2? What is this 2? Anyone, can you tell me? Why n by 2 power k? Okay, you can see T of n can be expressed as this part. It can be also expressed as this. Now, if we generalize this, you can see when we have a constant as 1, it is the denominator is 2. When we have constant as 2, the denominator is 4. So, substitute here, substitute k is equal to 1 here. Now, when substitute k is equal to 1 here. Now, what it will become? You can see it will become T of n by 2 plus order of 1, which is nothing but this equation. Now, substitute n is equal, k is equal to 2 here. So, it will become T of n by 2 power 2, that is 4, plus order of 2, big O of 2. This is nothing but this equation. And if you substitute k is equal to 3, it will become nothing but this equation. That's why this is the general expression. Okay. Okay, I know this is the base. Okay, it is the base of a logarithmic expression. But from where it came? Now, from where it came, can you tell me? So if we go back, okay, if we go to the back part, you can see from here it was generated. So it is because we are dividing our problem into half part in every step. This is also this you it is not that you can get log of n as recursive for recursive algorithms only. On iterative algorithms also, if you are doing iteration, in every step you are dividing the value of n with n by 2. So then also the time complexity will be log of n. Now I think you have studied this in mathematics, that log of n can be expressed as 1 n plus n by 2 plus n by 4 plus n by 8 up to it reaches 1. This is, I think, a result. Okay, so this we will see later. So yes, suppose if this algorithm was something like this, if it was not a binary search, it was a tertiary search. Means we were dividing the array into 3 parts in every step. So we are considering this part, again we are dividing into 3 parts. Then we are considering this part, again we are dividing into 3 parts. Now can you tell me, in this situation, what would have been the time complexity in terms of big O notation? Can you tell me? Anyone? Are you getting my question? Yeah, good. So Jasmeet and Nandita are very much correct. Vasmi is also correct. Now everyone is correct. Sahil is correct. It will be log of n base 3. So this 3 is the what we can say, it tells us that in how many steps our problem is divided in each step. Now I think it is good practice. We have seen some questions of time complexity. Okay. Now let me check if I have more questions. Yeah, we have exceptional questions. Shall we go till 8 o'clock? I want to cover it till today. Okay. Now we have a exceptional case when we have Fibonacci series. So everyone know, I will not write the code again. Everyone know the expression for Fibonacci series is this. Time complexity T of n can be expressed as T of n minus 1 plus T of n minus 2. And there is one constant also there, so I can write big of 1. So is everyone aware of this? We have done this yesterday. I think there isn't any confusion in this. Priyanka, I will just search on the internet and I will give you the links. Okay, just keep checking the announcement section. So the syllabus is so much vast now that I cannot include questions. I was trying to include questions, but it was taking the course to almost 3 months duration. From 40 classes, it was going to 80 to 60 classes if I started doing questions on every situation. But I was allowed to compress this class in 40 classes. That's why I have eliminated the practical part. But still I will share you links. Okay. So yeah, now let us solve this. Now you can see solving this is very difficult. Okay, this is a very, you can see many articles on this. It was a very tough. Many scientists tried to find the time complexity. But the easiest way is I am taking an assumption. I am taking that if finding the Fibonacci number at n minus 1 position. Okay, just take care. What I can say. Just understand this. My assumption is that if I find so okay, let me show you. If I am finding Fibonacci of 2, okay, let it be 3. It will be what? T of 2 plus T of 1. Now this T of 2 and T of 1 are only differing with one step. Okay, suppose if it would have been T of 2000 plus T of 2001. Now the time taken to find T of 2000 or Fibonacci number at the 2000th position, okay, 2000th position and at the 2001st position are both similar or not? They are similar. The time taken will be almost similar. It is not visible. I think it is visible. Okay, let me write somewhere else. This upper part is not visible to everyone because it is visible on the mobile phone. I can see on the app. Okay, so yes, I am telling that if I am finding the Fibonacci of a number like 2001, so I am writing as time complexity for this one. Won't it be similar to time complexity of 2000? Almost they would be similar. Okay, so that's why we can say that T of n minus 1 will be almost similar. This is t of n minus 1, means the time taken will be almost similar to t of n minus 2. This is the approximation which I am taking. Now this will simplify our problem statement. So now this statement can be converted to what? This statement can be converted to t of n is equal to nothing but 2 t of n minus 1 plus big O of 1. Okay, now I am not going much deeper. Now after the substitution methods only, you will get the next thing as 4t of n minus 2, and this will be 3 big O of 3 into, I can write it like this also, and I can write it as 3 into big O of 1, both are same, so I am writing it as 3 into big O of 1. Now again after substitution method, I am just skipping some parts. So we will get n minus 3 plus 7 into big O of 1. And similarly, now can you find the general expression? So the general expression was found to be this, that t of n. So don't worry, they will not ask you to derive this part in any exam. It is very difficult. So it came as like this, 2 power n minus, not like this, let me do this. Okay, it came like t of n is equal to 2 power k, t of n minus k, yes, now it's correct, plus 2 power k minus 1, this whole thing into big O of 1. This was the general expression. Okay, this was the general expression. Now, what is the base condition? Can you give me the base condition here? What is the base condition in Fibonacci when the recursion will stop? Okay, so we know that if you want to find the Fibonacci of the number 1, what is the result? It is n minus 1, that is 0. So the complex, how much time it is taking? It is taking order of 1. So can I write that t of 1? T of 1 is big O of 1. Is it making sense? Is this part making sense? You guys give a yes or no. Okay, great. Now we are trying to eliminate this time complexity in this term. So for that, what I can do, I can say that n minus k is equal to 1. It means what? Our k is equal to n minus 1. Now we are substituting this in this equation. So t of n will become what? 2 power k is replaced with n minus 1. So 2 power n minus 1. Now t n minus k is 1. So this is t of 1. Now 2 power k minus 1 can be written as 2 power n minus 1 into big O of 1. Shall I erase some part? Okay, let me write it here. Now this can we write it as 2 power n minus 1. T of 1 is nothing but big O of 1 plus, if we multiply this, so this is nothing but 2 power n minus 1 into big O of 1 minus 1 into this is big O of 1. I think it's clear. We have just multiplied, okay. This thing we have multiplied. Now this will become what? Okay, let me erase some part here. I am erasing some parts. Okay guys, just be with me. We are going to end it now. So this t of n, if we take 2 power n minus 1 common from here and here, so what it will become? It will become 2 power n minus 1 into big O plus 1 plus big O plus 1. Then we have minus big O of 1. Now these all things we can eliminate because these are constants. So it is nothing but 2 power n big O of 2 power n minus 1. So this can be written as big O of 2 power n by 2. Is it clear? Because we can express 2 power n minus 1 as 2 power n by 2. So this can be written as big O of 2 power n. So this is our answer. So the time complexity for Fibonacci number is big O of 2 power n. Any doubt? Okay, let me tell you an interesting thing. I will also share an article to you. I'm just writing it here. So actually this is not the actual answer. Okay, this answer we have got because we have taken as what? We have taken that this t of n minus 1 is almost similar to t of n minus 2. But it will be much less than this. Now what we got as the answer? We go of 2 power n. But the actual answer is, I have searched on internet, it's big O of 1.6180 to the power of n. Now this is less than 2, you can see. Now why we get a greater number? Slightly greater because we have taken this abbreviation. Okay, we have taken this function. So this is the actual answer, and this is known as the golden ratio. Golden ratio. And there was a huge calculation for finding this golden ratio. This is the actual time complexity for the recursive Fibonacci. Alright, so we have found this result. Now if we, any confusion? Now let me do one comparison here, okay. Let me erase all things outside. So we found that recursive Fibonacci has a time complexity as big O of 2 power n. But if we have a iterative approach, if we have a iterative code for this, okay, iterative Fibonacci only, so the time complexity would be order of n only. Now are you getting surprised? So it is the actual thing. Why? So you can see in recursive Fibonacci, why it is, you can see it is easily that this is greater and this is much lesser. Why? Because in using for loop, let us do a code. Okay, can you code it using okay, let me write it here. So for int I is equal to 0, I should be less than the, okay, it will take time. So the iterative code you can search on the net, that will take time complexity of order of n, because we are using a single loop. We will take two variables. Now why this is different? The difference is because suppose we are finding the Fibonacci of 5. So this is nothing but Fibonacci of 4 plus Fibonacci of 3. Now 4 is again but Fibonacci of 3 plus Fibonacci of 2, and this 3 is Fibonacci of 2 plus Fibonacci of 3. Now this 3 can be again written as Fibonacci of 2 plus Fibonacci of 1. Now here check, you can see the functions are again repeatedly calculating Fibonacci of 2. Again here also it is getting calculated again. Here also it is getting calculated again. 3 is also repeated. You can see 3 is here also, here also, here also. So this repetition increases the time taken for recursive approach. But in iteration, what we are going to do, we are just calculating. Suppose we have 0, 1, we add up, we get 1. We add last 2 digits, we get next digit. We add last 2 digits, we get next digit. Then we get 5. So this is an iterative approach. That's why it is taking order of big O of n. And the recursive approach is taking big O of 2 power n. So where the time is taken in these repeated function calls. Okay, so that is the actual reason why recursive Fibonacci is slower than iterative Fibonacci. So this can be a question in interviews in product-based company. This is a very critical thing, that why recursive Fibonacci is slower than iterative Fibonacci. Now, shall we do some more questions? Just tell me. I have, I think 1 or 2 questions more. Okay. So I am giving you a code. Tell me what is the time complexity. Okay, you have to find the time complexity. Let me erase it. Okay, the code is, okay, this is a simple if else. So first see, don't answer. This is if x is greater than 0, we have something in this if block which is having a big O notation of 1. Then else if this x is less than 0, we have something in this else block, in this else if block, which will give big O of log of n. Then else we have a block which have big O of n square. Are you getting this question? Means we have a if else ladder. Now if we have a value of x, suppose we have created a function which is accepting int x. This whole is inside the body of the function. Now if block is having some code, if this if block is working, that code will take order of 1 time complexity. In the else if block we have some code which will take order of log n time complexity. And in the else part, we have big O of n square, not order. Okay, big O of n square. Now we have to tell you what is the time complexity of this entire code in the terms of big O notation. You have to tell me this thing. I want to answer from everyone. Whether it is wrong, it doesn't matter. Just try to solve it. You don't have to do any calculations here. Firstly, it is an iterative thing. Not also iterative, it is a simple logical question. I need more answers. I need answers from everyone. I can see some are getting it correct. Okay, so basics are very much important. So you can easily answer this if you know the basics. What is the basics? The basic is that, okay, basics by which I mean the foundation. What is big O notation? It means the maximum time, means the worst case scenario. In the worst case, what will be that time complexity? So now you can see in the worst case what would happen. This block will run, which is having the maximum time complexity. It means what? When this will run, you can see this is in the else part, then this will not run, this will not run. So the time complexity will be big O of n square, because we are talking about the worst case scenario. Okay, is it clear? So those who have given this answer, big O of n square, are correct. Now I am giving you one more question. Let us see if you can answer it or not. So let me frame something like, if you have I is equal to 1. Okay, suppose this whole thing will be inside a function. I am not writing that, it will take time. Then we have a while loop. While I is greater than 0, then we are performing I is equal to I by 2. And okay, what is the time complexity of this code in the terms of big O notation? So now this is a trickier thing. Okay, good. I want to answer from all of you. I just not told this thing. What is 1 by 2? Pujita, why you have given 1 by 2? Okay. Now, okay, whenever you get these type of questions and you are finding difficulty in finding the answer, just assume some value. Okay. Now, let this I be a value as n. Okay. Now, suppose if we assume the value of n as 8. Now, in the next step, what will be the value of 8? It will be nothing but updated to 4. In the next step, it is nothing but 2. In the next step, it is nothing but 1. Now, isn't it similar? Now, what will be the total time taken for this? So, first, it will n, then n by 2, then n by 8, then n by 6. We can see in every step, it is getting reduced until we reaches to 1. So, if we sum up all this, it is nothing but uh, okay, the total time for all these operations is nothing but log of n base 2. Okay, so this is the correct answer. Now suppose if this statement, if I replace it with I is equal to I by 3. Now what will be the answer? What will be the time complexity? What will be the change in this time complexity? It will be big of, yeah, correct, log of n base 3. Good, good, good. Now if I add something, suppose, let me erase this part. If I add some statements in this code like I is equal to n, we have a is equal to 0 here, and we have a is equal to a plus I. Now tell me what will be the change in the time complexity. So this was the original time complexity. What will be the change in this? Okay, those are telling log n. I assume that you are trying to tell log n base 2 only. Same. Can anyone tell me, Nandita? Tell me what is the reason why it is same? Or anyone, those who are telling that it will be same, what is the reason behind that? I know you are correct. It will be same only. Okay. The reason, anyone? Because the statement, yeah. Divjal, you are correct. Naveen also correct. Good. Nandita is also correct. Everyone is correct. Now you can see, is this directly participating in the time? You can see this is what? This is big O of 1. Now here also we are updating this. This is also big O of 1. This statement is what? Big O of n. Okay, let me remove this. Now these two statements are doing any effect to the code? No. Okay, so these are just creating confusions for you. The main thing is which is inside this while loop, which is I, and I is getting operated. So yes, with this we end this class. Alright, so actually we have three methods. One is back substitution method. One is recurrence tree method. I think its name is. Another is master theorem. But I have shown you this back substitution method only because it is the most easiest method. And the other two methods are for the subjective purpose. I will give you the link. You can check that out. Okay, so I hope that you all learned something new today. Yes or no? And if you have any doubt, just ask me. Doubt, just ask me. Then I will end this class. Anyone? Any doubt? Okay, I think no doubt. So yes, thank you for listening with so much patience. I think we have a class tomorrow also. Yeah, tomorrow also we have a class at the same timing. A class, yes, this. Okay, I think the first class which we had, the introduction class. So there was some problem with that. Because of that problem, it is still under process. Okay, but the next classes you can see it was easily available. Yesterday class was available till 10 p.m. Okay, so this class is will also be available. Okay then, thank you for listening with so much patience. Let us meet tomorrow. If you have any doubt, you can reach me out. I've already provided the WhatsApp number. And good night.